So here let's stick to Matlab. I have to admit I'm a native in Matlab, so no Python here, but that's not a big difference for this application. So I read in the data from a CSV file. The data consists of closing prices of Bitcoins as features. So each data point is characterized by a closing price of Bitcoin, and I store this in a vector X. Then I normalize the vector such that the feature values are in the range 0 to 1. Then I read in the labels of the data points, which are the Ethereum closing prices at the same days, and then I normalize it. Okay. Then I apply polynomial regression. So polynomial regression amounts to trying to predict the label, so the Ethereum closing price, by using a polynomial evaluated for the feature value. Or equivalently, I have detailed this in the course book, polynomial regression amounts to first transforming the features into a feature vector. The feature vector is given by the powers of the feature. So this X here are the scalar Bitcoin prices. And I generate then polynomials or powers of this price. X to the power of 1, X to the power of 2, X to the power of 3, up to the maximum degree. So here the maximum degree is 6. So this loop generates all powers of the feature value up to the power of 6. And this defines a new feature vector. So each data point, a data point corresponds to one day. Instead of having one feature, which is the closing price, the Bitcoin closing price at that day, I have now a bunch of features, which are the powers of the Bitcoin closing price. And I can stack these new features into a feature vector. And it turns out polynomial regression is nothing but doing plain linear regression using this transformed features, using this new feature vector. Okay? Are there any questions on this? This is an important and very helpful insight how to transform or translate polynomial regression to an equivalent linear regression problem, but with different features. The feature vectors, you generate artificially feature vectors by computing powers of the original feature and stacking the powers into a new feature vector. Yes? So the question was, what does this power computing does? Well, it allows you to represent maps from features to labels which are not linear, but like non-linear, like polynomial curves. So you exactly, the more powers you use, the more variation you can model in the map between features and labels. And if you look at the scatter plot of the data, so I have here then plotted a few data points. So these circles here, these blue circles denote the training data or some of the data points. And they are not really kind of fitting, you cannot fit a curve, a linear curve there nicely. If you look at the first few, they are very flat, almost no slope. And then all of a sudden, you have a rather discontinuous change to a new range where the y values are way higher. So the data kind of doesn't look linear. The relationship between features and labels, as observed in the scatter plot, doesn't suggest that a linear function does a good job in fitting the Bitcoin and Ethereum prices. That's why we try out now polynomials. And the question was, if I use larger degree polynomials, can I ever end up with a larger training error? So the training error, remember, we then, after setting up the features, we want to find that particular hypothesis which predicts the labels on the training set as good as possible. And how good we measure, or how good it does this job, we measure using the squared error loss. And if you write this down, this amounts to an optimization problem. This is called an empirical risk minimization problem. It turns out you can solve it closed form under some conditions. It turns out you can solve it using this matrix equation here. or in Matlab notation, you have to invert a quadratic of the feature matrix and multiply it with, again, with the transpose of the feature matrix and with the label vector. So this vector y here contains the labels of the training data points. And this matrix X poly here contains the new feature vectors of the training data. So this weight vector here, which you compute, is a closed form solution, tells you how to optimally combine the powers of the features to best fit these blue points here. And you see, so the result of this fit is this yellow brownish curve, which is the closed form solution. And you see this curve, this polynomial fits the data points pretty well. Some data points almost lie exactly on this curve. Okay? Another method for finding this optimal weight vector is gradient descent. So I have here below the gradient descent solution. So you do gradient descent for a linear regression problem, for a particular linear regression problem here. That is the linear regression problem involving these transformed feature vectors. But it's then a linear regression problem, and all the tricks, all the gradient descent knowledge and wisdom you have, you can apply here and do gradient descent for polynomial regression. Then you get another weight vector, typically. In theory, when you repeat these gradient descent steps for a sufficiently large number of times, this weight vector gets more and more close to this optimal solution. However, it typically does not reach it exactly because gradient descent is only an iterative method which makes some progress, but you need to do more and more and more steps in order to get closer and closer. But for some reasons, and in many applications, it is not necessary to get this exact solution perfectly, but a close enough solution is good. And you see this here, this violet curve is the predictor, the polynomial, that is obtained using the the weight vector delivered by gradient descent using a fixed number of iterations. And it's clearly different from the closed form solution, from the yellow curve, which is way more wobbly. And we see, for example, that this gradient descent solution does not fit as good these blue circles, which are used for the training, which are used as the data set to minimize the empirical risk. And for these data points, which are the blue circles here, this gradient descent curve, this gradient descent solution is not as good as the closed form solution. So it seems closed form solution is the best. So it perfectly, this closed form solution almost perfectly matches the training data. It achieves almost zero error. However, this is true only in theory if you are able to perfectly compute the matrix inverse here. Okay? As soon as this matrix here inside this inverse is ill-conditioned, which means that kind of the ratio between largest eigenvalue and smallest eigenvalue is extremely large, then this inversion will be unstable. In particular, you have observed then in the Python notebook for exercise 2 that although you increase the degree, so you have more powerful hypothesis spaces, the training error becomes larger because it's not able to solve this polynomial regression problem anymore and just outputs random noise. Let's try out here a very large degree, like 12. Yeah, the blue curve again is the output of the closed form solution, and we see it kind of explodes. So the data points, no data point is anywhere as large on the y-axis or as far on the y-axis as this closed form solution. So this closed form solution for polynomial regression becomes highly unstable, and even on the data points, on these blue circles, it's off. So I need to zoom in a lot. So here even this yellow curve should be theoretically perfectly on the training point, which we use for fitting these polynomials, but it doesn't achieve it anymore simply because it cannot compute the inverse accurately enough. And that's why you didn't this Python notebook was misleading for answering the question of how the training error behaves when you increase the polynomial degree. In theory, increasing the polynomial degree can only reduce the empirical risk on the training error because you have more hypotheses which you can choose from to fit the training points. However, the numerical errors induced in a computational framework like Python or Matlab make it useless, this approach. So this closed form solution is often useless in practice. However, this cheap gradient descent algorithm, which just amounts to updating the weight vector a sufficient number of times, it works. This cheap gradient descent. We have one particular example for degree 6. Yeah, so the yellow curve again is the closed form solution, which does a very good job on some of the training data points with the blue circles, but yields very kind of unstable predictors, very wobbly. In contrast, gradient descent does not as good fit the training data points because it's only a suboptimal solution. However, it has kind of an intrinsic regularization, which means that the polynomials delivered by the gradient descent solution are smooth, are relatively smooth. They are not as wobbly as those obtained from the closed form solution. And this is actually nice because I also show as crosses a few other data points which are not used for training, for selecting a good predictor. I have kept some data points aside which I didn't use for choosing a good polynomial. And this I show now. These are the one with the red cross, and it turns out that the suboptimal solution on the training data set provided by gradient descent does a way better job also to predict or to work well for the red crosses here, for the data which has not been used to train the data. And we will see then in the next exercise round that this is exactly what we want to do, or what we want to have. We want to have that the hypothesis or the predictor map that we learn when we solve the empirical risk minimization problem, in which you did now using gradient descent or a closed form solution, we want this hypothesis that we get from this training phase to work well on new data. And we call this, in this case, validation data. So we learn a hypothesis or a predictor on training data and then evaluate it for new data, validation data, and these are the red crosses here. And if the training error is small, but the error on new data is large, then we call this situation overfitting, which is one of the key obstacles in having successful machine learning applications. You want to avoid overfitting by any means. So let us look at this yellow curve, which is obtained by fitting a polynomial to the training data, these blue dots, as good as possible. So we want to minimize the training error as much as possible, and we do this using this closed form solution. And it does really a good job. I mean, this yellow curve almost passes through all the blue dots here. So the training error is almost zero. There's no deviation on the training data between the predicted y value and the true y value. It's very little, this deviation here, this vertical deviation, which defines the training error. However, if we look at the error for new data given by the red crosses, well here, for example, this red cross is very poorly predicted by this polynomial regressor. This polynomial regressor here, or predictor, overfits. And we want to avoid this overfitting. And how do we avoid this overfitting? Well, the first thing is to detect the overfitting and then try to use less complicated functions to reduce the complexity of the hypothesis space. For example, use smaller degrees for the polynomials. This will be the main theme of the next exercise round starting next week, which is called model validation and model selection. Okay, any questions on this? So confusion was now caused because the theoretic kind of solution for polynomial regression required to invert matrices which cannot be inverted accurate enough using, for example, Python. You need to come up with highly specified algorithms to invert such badly conditioned matrices. On the other hand, if you use gradient descent, you don't have any such problems. Gradient descent works for feature matrices which are not invertible, and works also for feature matrices which are extremely ill-conditioned. However, as soon as you want to invert an ill-conditioned matrix using a standard function of Matlab or Python, you get erratic results. Yes?
What do you mean by
Ill-conditioned? So you can characterize the difficulty for inverting a matrix. Like for linear regression, we have to invert this matrix here. So this is a symmetric matrix. It's positive semi-definite. So I can plot it here, looks like this. And a measure for how difficult it is to invert this matrix is the condition number. And the condition number you can estimate using cond. The condition number is always larger or equal than 1, and 1 is the best case. 1 is basically an identity matrix, and inverting an identity matrix is easy. But this here has a condition number to the power 10 to the power of 10. And when you have 10 to the power of 10, it's still okay, it's on the limit. But when you then have 10 to the power of 20 condition numbers, you basically get nonsense out of a standard purpose matrix inversion function in Matlab or in Python. So let's see what the condition number is for max degree 20. (10 to the power of 17). So it grows pretty fast. And I mean, 20 is not really large. You can, let's try 100. Let's see when it breaks. Oh, 10 to the power of 19. So Matlab seems to be more stable than Python for this case. And no wonder Matlab is specialized for matrix computations. Infinite. Now we broke it. So for a degree 1000, the precision that you need to invert the matrix is beyond the capabilities of my MacBook. And these are not really large problems. I mean, dimension of thousands is nothing for a machine learning problem nowadays. However, this problem is only for the closed form solution. Gradient descent works like a charm, still. And this was also one of the key messages yesterday in the guest talk on deep networks. The method to use to select a good hypothesis, which means a good configuration of weights inside an artificial neural networks, are variants of gradient descent. Okay, any other questions? Yeah, then we still have 3 TAs present, which you can ask for face-to-face consultation. Thanks a lot.